Good day, folks. Welcome to my YouTube channel. If you're new here, please don't watch my video without subscribing. Please subscribe first. It's absolutely free and you do not pay anything when you subscribe to my channel. You're just supporting me when you press the subscribe button and then the notification button. If it's still there, I'm not sure. It will notify you every time when I upload a video. If you're enjoying my videos, please subscribe, guys. 68% of you are watching my video without subscribing. Please, guys, I beg you. Right. Now today we're going to look at organic chemistry. In organic chemistry, we're going to look at question 4. The last question of the organic chemistry. We're going to look at physical properties and intermolecular forces of organic compounds, right? So first thing that is important here, what are the physical properties? When we talk about the physical properties, there are 3 of them. It's the melting point, boiling point, and vapor pressure. I'm not going to dwell on the definitions of them. When it comes to the definitions, you have to look at the exam guidelines. Strictly exam guidelines, they give you definitions there. Now, the physical properties, they depend on the strength of the intermolecular forces. The intermolecular forces that we're going to look at, they are hydrogen bonding and the London forces and the dipole. London forces is the weakest, and then the strongest is the hydrogen bonding, and then followed by the dipole. And we know the hydrogen bonding is the type of a dipole, right? Sorry, guys. Now we say the physical property depends on the strength of the intermolecular force, and the strength of the intermolecular force increases with the increase in boiling point, or lower vapor pressure, or higher melting point. If a substance has a higher boiling point, that means it has a greater intermolecular force. If a substance has a lower vapor pressure, that means it has the higher melting point, right? Guys, you do not say, since I say increase in boiling point, increase in strength of intermolecular force, you do not say they directly proportional. They're not directly proportional. If you say they're directly proportional, you lose marks. So do not say that. So the lower the vapor pressure, the greater or the stronger the intermolecular force of the substance. The higher the boiling point, the stronger the substance. Now, this side you could say they are inversely proportional, but you do not say that. The strength of the intermolecular forces decreases with a lower boiling point and higher vapor pressure and lower melting point. If a substance has a lower melting point, that means it has a weaker intermolecular force, which is the weaker intermolecular force is going to be the London, and higher vapor pressure, weaker intermolecular force, lower boiling point, weaker intermolecular force, right? Now, the strength of the intermolecular force depend on the 3 things, which is the chain length, the functional group, or the homologous series. And also, but when we talk about the functional group, we're talking about the homologous series as well, and the branching and compactness. We're going to talk about that. Now, the strength of intermolecular force depend on the chain length. How is it depending on the chain length? If a substance increases the number of carbons, right? It increases the number of carbons. That means the chain is becoming longer, right? So if the chain is becoming longer, that means the larger the surface area is becoming bigger. It has one carbon, and then another has 2 carbon, and another has 3 carbon. That means the surface area is getting larger, the chain is getting longer. That means the stronger the intermolecular force. The more the number of carbon increases, the larger the surface area, the longer the chain length. That means stronger intermolecular force. and then there will be more energy that is needed. The more the intermolecular force are becoming stronger, there will be more energy needed to overcome the intermolecular force between the substance, and that means it has a higher boiling point and the lower vapor pressure and higher melting point. Remember guys, when a substance has a stronger intermolecular force, it means it has a lower vapor pressure. Don't say it has a higher, because it's a higher boiling point and higher melting point, but the vapor pressure is low for that. Remember guys, that's very important. And then the substance, the more the substance is branching, which means it had 3 carbons, and then let's say it has 4 carbon, and now you change these 4 carbons and you make them a branch. It's going to be 4 carbons like this now. So that means this substance is branching, right? The more the substance is branching, the smaller the surface area. The smaller the surface area, the weaker the intermolecular force. That means less energy needed to overcome the intermolecular force on that substance. And that means lower boiling point, lower melting point, and the vapor pressure is what? Is higher. So the intermolecular force decreases in this side and the intermolecular force increases in this side. More branching, smaller surface area, weaker intermolecular force, less energy needed, lower boiling point, lower melting point, higher vapor pressure, right? When it comes to the functional group or the homologous series, we know all the homologous series. Now, the alkane, alkene, alkyne, right? They have the weak intermolecular force, which we call what? London. In fact, all of them, they have the London force, but as we go up, the strength of the London is what? Is weaker. The is weaker when we go to this side. So the alkane, alkene, alkynes, they have the London force. You see, all of them they have, so they only have the London force, right? And then, which is the weakest intermolecular force. But as you go this way, the strength of the London is increasing, right? The alkynes have a strongest intermolecular force among these ones, and then followed by the alkene, and then the weakest is the alkane, right? Now let's go to aldehydes, ketones, and ester and haloalkane. Even them, the strength of the London is increasing when you go to that side. Even generally, their strength it is increasing, when you go this way. All right. Now in this one, we're going to look at the it has the London. These ones, they have the London force, but in this London force, the strongest intermolecular force that they have in addition to London is the what? Is the dipole. Dipole. These molecules are polar. This is polar, 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 all of them. So if they are polar, they have a dipole force, right? Since they have the dipole force, so two forces on them. It's the London force and the dipole. And then lastly, we have the alcohols and the carboxylic acids. Remember guys, I said the strength it increases this way. Alcohol and carboxylic acids, they in addition, they have their London force, but in addition to a London force, they have a dipole, but that type dipole is the hydrogen bonding, right? This type of dipole they have, that is the hydrogen bonding. So remember, the hydrogen bonding, it occurs in north. What is north? When there's a nitrogen, there's a oxygen, there's a fluorine. So these ones they do have, but the difference between these two, this hydrogen bonding there's a difference between these hydrogen bondings between the two, but I'm going to dwell on that. So the ones with the strongest is these two, they have a hydrogen bonding. Here's the explanation of the difference in those hydrogen bonding. If you look at this ones, it's alcohol. Alcohol, it says they have one side for hydrogen bonding. Here's an alcohol molecule, and here's another alcohol compound, right? So if you see here in alcohol, there's a OH, and at that compound there's a OH. So the oxygen of that compound, it bonds, or it is attracted to that hydrogen of the other compound. So the H and O bond, we call it a hydrogen bonding, and there's only one hydrogen bonding between the alcohol molecule. That's why we say it's a one side. But in carboxylic acids, you see, here's a carboxylic acid. How do we see it? We see it by the functional group there. And there's another carboxylic acid there. The same compound. Do you see there's a OH, which is the hydrogen bonding, and there's a hydrogen bonding there. So those two hydrogen bonding, we call them two sides hydrogen bonding. The two sides hydrogen bonding, which means it's two hydrogen bonding. So the two sides hydrogen bonding is stronger than the one side hydrogen bonding. It's the bond, so it needs more energy to break this bond, but in this one it just requires lesser energy than this one. So carboxylic acids are two sides hydrogen bonding. It's very important, guys, to keep that in mind when you compare the alcohol and acids all the time. Okay, guys, now let's look at the most important part of this question 4 of organic chemistry, on how we explain the difference in physical properties. We know when our physical properties is the boiling point, melting point, and vapor pressure. How do we explain the difference in organic compounds? Right, guys, these are the steps that are very important when it comes to explain the difference in physical properties of any organic compounds when you are given. Maybe they're in the form of a table or whatever. This is how you explain it. This is the structure. It's very important. Step number 1, you state the difference in terms of structure. So if you see all of them, they have a difference in chain length. When we talk about chain length, or we see the difference in what, in branching, or they differ in functional group. That's the first thing you talk about them, right? They differ in chain length or the surface area or the branching or the functional group. That's what you talk about them in point number 1. When you explain here, guys, you explain in bulletin form, in point forms, not writing big paragraphs here. So you state the difference in structure, which is the chain length, branching, or functional group responsible for the difference in boiling point. That's all you talk about. And then point number 2, you state the effect of the factor in intermolecular force. So you say there, let's say you said the structure of one, it has a chain length than the structure of B. The structure of A has a longer chain length than the structure of B, and then you stated the intermolecular force. The one that has a longer chain length, it has a stronger intermolecular force. You can state even the intermolecular force if you want, or you say structure A is more branched than structure B. Structure A is more branched than structure B. That means structure A, if it's more branched, it has a lower or a weaker intermolecular force, right? Or the functional groups, you say, if you say that compound A is an alcohol, and compound B is an alkane. So you stated the effect of the intermolecular force there, and you say the one with the alcohol, it has a stronger intermolecular force than the one, the alkane. You'll see, guys, I'll show you examples, and then state the effect of energy. the effect of energy, you will say more energy needed to overcome the intermolecular force, not to break the bond, guys. You can't say here more energy needed to break the bond. You're going to be wrong to say that, guys. Let's look at the example of that. Now, example number one, it says explain an increase in boiling point from a methane to butane. I'd like you to draw this one, to draw you this one. From methane to butane, let's say this is methane and this is ethane, and this is propane, and this is butane, right? Very important, guys. Looking here, you can explain in terms of structure, because they're the same homologous series, this compound, right? Same homologous series, but what are they differ by? They differ by the chain length, right? They differ by the chain length is ethane, methane, ethane, propane, butane. So the first thing that you do, you say step number one, you talk about the difference in structure. Increase in chain length from methane to butane. That's point number one. There's an increase in chain length. Or you can say there's an increase in what? In surface area. Or you can say the number of carbon are increasing from methane to butane. But the best one to say is to increase in what? In chain length. That chain length are increasing there due to the increase in number of carbon. Point number two. From methane to butane, you say the increase in strength of what? London, or intermolecular force from methane to butane. If you're looking here, as the surface area increases, the strength of the intermolecular force is what? Is increasing, right? That's very important. And then from methane to butane, more energy needed to overcome the intermolecular force. Thus, there's an increase in boiling point there. There's an increase in boiling. So the important points are these ones there, right? Very important, guys. Now let's look at example number two. Example number two, we are given, it says explain an increase in boiling point from compound A to compound B. Now if you look at compound A, B, C, right, compound A to B, C, we are given the boiling points there. The boiling points, they tells us the higher the boiling point, the stronger the intermolecular force. So that means the intermolecular force is getting stronger from A to what? To C. What causes that? It's the branching and the chain length. Is the branching and chain length there. So the difference in these structures, if you look at them, all of them, they have same homologous series. So what makes them differ is the branching. Let me draw you compound A. Here's compound A. It's 2,2 dimethyl propane. Here's compound A. Do you see? It's like that. It's 2,2 dimethyl propane. And compound B, it's like that. It's 2-methyl butane. There's a methyl here. It's like that. Methylene 2 and C. It's going to be like that. It's pentane. Right, so the difference here, they have the same homologous series. These compound, guys, what makes them different is the chain length and the branching. So as you move from C to A, it's becoming more branched, and the chain length decreases. Right, but now the way you're going to put it, as we can see, the boiling point, it tells us the intermolecular force. The higher the boiling point, the higher the stronger the intermolecular force. So you will say step number one, you talk about the structure of them. Increase in chain length from A to C. It's becoming less branched there. So as the more it's becoming less branched, is the more that the chain length increases. If you can see here, chain length is smaller, it's becoming bigger, and more bigger. The chain length increases from A to C or decreases the branching from A to C. The branching is decreasing there. So the strength of intermolecular forces increases, which is the London. All they are all alkanes, so the force is London, and then there will be more energy needed to overcome intermolecular forces from A to C. I hope that makes sense. Now let's look at example 3. Example 3, it says explain the increase in boiling point from compound A to compound C by referring to the type of intermolecular force. When they tell you by referring to the type of intermolecular force, so you state their intermolecular force, each of them. Now, if you look at these compound A to C, we have butane, which is an alkane, and we have propane 1O, which is it's a alcohol, and ethanoic acid, it's an acid. And if you can see their molecular mass, they are equivalent. This 58, it's almost the same as 60, so their molecular mass are equivalent, and their boiling point, they're different. As you move from A to C, the boiling point increases. It tells us about the intermolecular force there. So here, when they tell you by referring to the type of intermolecular force, you should, first thing that you need to state, which is bulletin number 1, it's the intermolecular force of them. So butane is an alkane, it has the London force, and the propane 1O is an alcohol, it has a one-side hydrogen bonding. An ethanoic acid, it's a carboxylic acid, it has a two-side hydrogen bonding. So the reason to state that this is a one-side hydrogen bonding and two-side hydrogen bonding, because both of them, they are hydrogen bonding. But if there was only alcohol, no acid, there was no need to say it's one side, you will just say hydrogen bonding. But now, to say two sides and one side, you are differentiating this type of hydrogen bonding. And then now, after you've stated this is 1 mark, all these first 3 points, it's 1 mark. After you stated their intermolecular forces, and the point now you compare their strength of intermolecular force. So you say strength of intermolecular force increases from A to C. It increases from A to C, because the weakest is the alkane, and then followed by the one side, and then the strongest is going to be the carboxylic acid, and then more energy is needed to overcome the intermolecular force. I hope that, guys, makes sense. Let's look at the variables, the independent and dependent variable and the control variable. Now, the independent variable, guys, it what makes the compound different. If you look here, you have compound A to D, and they are the same homologous series. It's carboxylic acids, all of them. So the independent variable, it's what makes them different. What makes them different there? If you see, there's 1 carbon, 2 carbon, 3 carbon, 4 carbons, right? So it's the chain length that is going to be an independent variable here, and always the dependent variable is the physical property that you are given here. We are given here the boiling point, so that's the dependent variable. It will be the boiling point. So the boiling point, it's always the dependent variable. In fact, any of the physical properties such as boiling point, vapor pressure, melting point, all they are their physical property. But in this case, since we're given the boiling point, it will be the boiling point. Independent variable is the chain length. Now let's look at this one. This one, we are given the boiling point again, is the dependent variable. But here we are given the isomers. The isomers, they differ by the structure, by their structure. So if you look here, what makes them different? This one is it's not the functional group, they have the same functional group. So what makes them different is the chain length as well, or the surface area, right? And the independent variable, that's the independent variable. Dependent is that, and the control variable here, it's what is the same. The control variable, it will be the functional group here, because they have the same functional group or same homologous series, right? Now if you look at this one, now Now it says if the compounds are not having the same functional group or homologous series, independent variable is the functional group. If you look here, this is an alkane and a ketone, an alcohol, and an acid. So what makes them different? This is an independent variable. So the independent variable here is the functional group or the homologous series, right? And the dependent variable, it will be the the vapor pressure, right? And the control variable always, guys, is anything that is the same, like the molecular mass. If the molecular mass of these are the same, sorry, that's the control variable. It's 4 carbons and it's 3 and it's 3 and it's 2. So here the control variable, it's anything that is the same here, but we don't have them. We have a carboxylic acids and we're given the boiling point. So the independent variable here, it will be the chain length, and then the dependent variable, it will be the boiling point, and the control variable is the functional group, because they're the same with the functional group. Here we have isomers here, A to C, and then we have boiling point. So the dependent variable, it will be the boiling point, and the independent variable here, it will be the surface area, which is the chain length, which is the branching, and the control variable, it will be the molecular mass. Their molecular mass is going to be the same because they are isomers. If you remember, isomers, they have the same molecular mass. And in this one, we have different homologous series, so, or different functional groups. So the independent variable, it will be the functional group, and the dependent variable, it will be the vapor pressure. And then the control variable is difficult in this one, but you have to focus on comparing two molecules. For example, these are the ones, it's B and C, right? When I'm looking at this one, B and C, they have the same chain length, so you can compare with this one, these two, in terms of the control variable. Remember, the control variable, it's what is the same. It's B and C, they have the same chain length.